Okay, those of you on Zoom, can you hear me?
Yeah.
Can you hear me? Right, we're going to take a look at chapter 9. I just got started on this last time. We'll review quickly. Okay, some of the main points here. With alkynes, there are two elements of unsaturation for each triple bond. Some reactions resemble the reactions of alkenes, like addition and oxidation, and then there's some that are specific to alkynes. Alkynes will end in YNE. Okay, so this is but1-ine, but2-ine. Some common names are used commercially as substituted acetylenes. The physical properties of alkynes are similar to those of alkenes and alkanes. Are nonpolar and soluble in water, but they are soluble in most organic solvents. The first four, at least up to 4 carbons, are gases at room temperature. Alkynes are less dense in water.
Dr. Trump.
Ethine is used in cutting and welding torches. It's first mixed with oxygen before it's burned. It burns with a very hot flame. Acetylene can be prepared either from coal or natural gas. Okay, it contains a triple bond. Two sp orbitals overlap to form a sigma bond, and then we have 2 pi bonds.
Dr. Trump, could you share your screen with us?
The triple bond is shorter, stronger, and stiffer than a double bond. And also CH bonds to sp carbons are shorter than those to sp2 or sp3 carbons. Okay, this is one major difference between alkynes and other types of hydrocarbons. And that is, if the alkyne is at the end of a chain, or we're talking about acetylene, this hydrogen is unusually acidic. Okay, it's not acidic enough where we can remove it with alkoxide or hydroxide, but we could remove it from NH2 minus. Okay, because ammonia is a weaker acid than acetylene. Okay, I'll show you this slide. Again, we can use sodium amide, also called sodamide. All right, this works. This removes the hydrogen. We get the conjugate base. And then the conjugate acid of NH2 minus is ammonia. If there's no acetyletic hydrogens, that is, if the alkyne group is in the middle of a chain, then it won't react with NaNH2. Okay, because these hydrogens are about the same value as other alkanes, so they're about 50 for the pKa. So nothing will happen with but2I. Okay, this just tells you how to make sodamide or sodium amide. These acetylite ions are good nucleophiles. They can be used in SN2 reactions to lengthen the chain. The substrate has to be either primary or methyl. Okay, otherwise you get E2 elimination if it's secondary or tertiary. Okay, here's an
Dr.
example
Trump?
of secondary halide. We end up with the elimination product.
Dr. Trump,
If we start with acetylene, we can lengthen both sides one at a time. Okay, so here we're adding 6 carbons to this side and 2 carbons to this other side. Okay, another reaction we can do with acetylite ions is we can attack the carbonyl carbon. If we start with a ketone, the carbon is electron deficient. It has a partial positive charge, and so that attracts a negative charge. We form a bond here, and then once this reaction is done, then we add dilute acid, and that gives us an acetyletic alcohol. Right, we have to wait till this reaction is done, because if we introduce the hydronium too soon, the acetylite ion will simply pick up a proton from the hydronium. Okay, if we use an aldehyde instead of a ketone, very similar reaction. We get a secondary acetyletic alcohol, except instead of a tertiary. Okay, here's a specific example. We have this ketone, cyclohexanone. All right, our acetylite ion will attack the carbon, push a pair of electrons up onto the oxygen. And then when this first reaction is complete, then we protonate. Okay, so this is called 1-ethynyl cyclohexanol. Okay, this is just working backwards. Okay, if we see an acetyletic alcohol like this, okay, working backwards, we break this bond. Okay, so this part of it would be the acetylite ion, and then we make this a double bond to get our starting materials. Alkynes are often prepared from elimination reactions. Right, we can do a double E2 elimination with molten or fused KOH at 200 degrees. If there's more than one alkyne that could be formed, molten KOH is going to favor the internal alkyne, while sodium amide at 150 degrees, followed by water, favors the terminal alkyne. Okay, so here's one example. Okay, we do a double E2 elimination. Okay, OH removes the hydrogen, form a double bond, kick out the bromide. Then we go this way. OH removes the hydrogen, we form the double bond, we kick out this other bromide. Okay, so the two main sources of alkynes, of course, are acetylene that we can get commercially. We could also prepare alkynes by double elimination reactions. Just like alkenes, okay, we had a lot of these in the last chapter, addition reactions. You can have addition reactions. In some cases, the alkyne can add once or twice. It's usually exothermic. Hydrogen adds twice to an alkyne to form an alkane with nickel, palladium, or platinum. If we use this partially deactivated catalyst, we can obtain the cis alkene. Okay, so this is stereo selective. We do get the cis. Okay, what if we want the trans? Okay, so this is something we didn't cover last time.
Dr. Trump.
Okay, so what we can use here is sodium and liquid ammonia. Okay, that's not to be confused with NaNH2. Notice there's a subtle difference here. This is not the same as sodium amide. This is just sodium, sodium metal. And this gives us the trans alkene. Okay, so using a dry ice bath, you keep ammonia liquid. Ammonia is normally a gas at room temperature, but its boiling point is somewhere around -38. You'll add sodium metal to the ammonia, and it will lose an electron. I'm sharing my screen. Okay, there we go. Okay, so let me back up. I'm sharing my screen now. Okay, so let me back up a couple slides. Okay, if we use nickel, palladium, or platinum, it's really not possible to stop at just one hydrogenation. We can't isolate the intermediate alkene. This goes all the way to the alkane. If we use Lindlar catalyst, we can stop at the alkene. Specifically, this gives us the cis. Okay, and then this is a method of preparing a trans alkene, the liquid metal ammonia method. Okay, so the sodium metal dissolves in the ammonia, liquid ammonia, and it loses an electron. Right, this electron then, this free electron then becomes solvated, and that results in a deep blue solution. Okay, so sodium lost an electron, so now it carries a plus charge. All right, here's how that works. All right, so we've got a free electron here. And the free electron adds to one side of the alkyne. Okay, notice the single barbed arrow here. That's a single electron. And that causes a pair of electrons to be pushed over to the other side. Okay, this was neutral. It gained an electron. it gained an electron, and that gives us a radical anion. It's negative because of the gain of one electron. And this orbital takes up a lot of space, and so does this one. And so these two orbitals need to be trans to each other. All right, what happens next is that the lone pair with the negative charge then grabs a proton from ammonia, which is the solvent, and that gives us this vinyl radical. And then the last two steps are a repeat. Another electron joins this single electron to produce a vinyl anion. That vinyl anion picks up a proton from another ammonia molecule, and our product is a transalkene. Chlorine and bromine can add to alkynes to form vinyl dihalides. They may add cis, syn, or anti, so the product is a mixture of cis and trans isomers. It is often difficult to stop at just one addition. In other words, this has a double bond, so it can actually add another equivalent. Okay, if we use 2 moles, then it goes all the way to the tetrahalide. Okay, we can also add HX, where X is chlorine, bromine, or iodine, just like we did with alkenes. If 2 moles are added, then the product is what we call a geminal dihalide. Okay, both 1 and 2 equivalents will follow Markovnikov's rule. Okay, so for example, we have pent-1-ine. One position is richer in hydrogen, so that side gets the hydrogen. So this is the Markovnikov product. Okay, if we add another equivalent, of HBr. Again, H goes to the side that's richer, and bromine will go to carbon number 2. Okay, here, neither side is richer in hydrogen, and so we'll get a mixture of products. Okay, the H could go here, the Br could go to 3, the H could go to 3, the Br could go to 2. So we get both of these. Okay, but if we have a terminal alkyne, it's going to be regioselective. So follow Markovnikov's rule. Okay, so the mechanism is the same as for alkenes. Triple bond picks up an H, the halide adds to the plus charge, and we get our addition product. Okay, you may recall that we could add HBr in anti-Markovnikov fashion if peroxides are present. Turns out that also applies to alkynes. Okay, if we have a terminal alkyne. Okay, if it's an internal alkyne, since there's no hydrogens on the alkyne group, it won't make any difference. Here we have pent-1-ine, which is a terminal alkyne, and HBr will add an anti-Markovnikov fashion. Okay, and it's not stereo selective, so we'll get both E and Z isomers here. We can hydrate an alkyne using mercury 2 sulfate. This gives us a, if it's an internal alkyne or even a terminal alkyne, it'll give us a ketone. Okay, if we're adding water to an alkene, we'll add H to one side, OH to the other. Okay, that's what we have here in brackets. Okay, we have H to one side, OH to the other side. This follows Markovnikov's rule. Carbon number 1 is richer, so that gets richer. This is an enol. Most enols are not stable. An enol is a compound in which an alcohol is directly attached to an alkene. Okay, there are some exceptions, but in general, most enols are not stable. And so this will undergo a rearrangement to a ketone. Okay, these are not resonant structures because the position of the hydrogen has changed. Okay, so the hydrogen moves over here, double bond moves over here. Okay, water is actually what adds, but mercury 2 is the catalyst. Now this equilibrium, this is not resonance again, right? This equilibrium is called tautomerism. Okay. As I said, most enols are not stable. They isomerize to the corresponding aldehyde or ketone. Okay, this is the mechanism for tautomerism. Okay, if we have just a trace of acid, the alkene picks up that proton. Okay, so the proton goes to the side that's richer, which is here. The other side gets the plus charge, and this is now resonance stabilized. The plus charge can be delocalized between carbon and oxygen. And then, in the next step, water takes off that proton, we get our ketone. All right, the other anti-Markovnikov reaction besides HBr and peroxides was hydroboration oxidation. Okay, we can also do hydroboration oxidation of alkynes, but we need a different reagent. Okay, so what is commonly, there are others of these that can be used. This is probably the most common. This one is called dicyamal borane. And this is the secondary isoamyl or cyamal group. Okay, so you have 2 of these. And the idea here is to make this borane really hindered. Okay, you attach these 2 bulky groups. And unlike BH3THF, there's just one hydride equivalent, not 3. Okay. If you were to use borane THF, this would go all the way to the alcohol, which I guess is okay if that's what you want. If you want an aldehyde or ketone, then you'd use dicyamal borane. Okay, so this adds, here we have we start with a terminal alkyne. The boron adds to carbon number 1, hydrogen adds to carbon number 2, and then when we oxidize that, we get an aldehyde. Okay, if the alkyne is internal, then we get a ketone. Okay, again, we form an enol and it tautomerizes to an aldehyde. This is base catalyzed tautomerization. This is how that works. Hydroxide deprotonates the enol. The enol is pretty acidic. We get this enolate ion. The anion then grabs a hydrogen from water. We get the aldehyde. All right, the oxidation of alkynes is similar to the oxidation of alkenes. Okay, if we do oxidation with a dilute neutral solution of KMNO4, that will oxidize alkynes to a diketone. Okay, with an alkene, remember we got a diol. Warm basic KMNO4 will completely cleave the triple bond. Ozonolysis also cleaves the triple bond. Okay, so when we have an alkene, we add two hydroxyl groups with cold dilute KMNO4. And then, because this is a triple bond, we add two more. This intermediate is unstable. It immediately loses two waters to give us a diketone. Okay, if we use hot KMNO4 or warm KMNO4, okay, that completely splits the triple bond. Whoops. That completely splits the triple bond, and we'll get two carboxylic acids. Since it's in basic solution, we'll get the conjugate base. We'll get carboxylates. If we add a strong acid, such as HCl or sulfuric acid, we'll get two carboxylic acids. Okay, ozonolysis also cleaves a triple bond. And then if the triple bond is at the end of a chain, we end up with carbon dioxide as one of the products. Right. That concludes chapter 9. Okay, what I'm going to do next, stop sharing, and I'm going to do some practice drills. Okay, I'm going to write a question on the board, take out some writing paper and something to write with. I'm not going to check your answers. I'm just going to write the question, wait a few seconds, and then I'll give you the answer. Don't simply just wait for the answer. Do try to solve the problem. Okay. If you just wait for the answer, that's not going to benefit you much. Okay, so backing up to the previous chapter, make sure that I'm on screen here. Okay, going back to the previous chapter. Okay. I'm asking for the product here. Right, this is methylene cyclopentane. And if we add HBr to it, okay, what do we get for the product? Okay, so write down the answer. Okay, this is an addition reaction. There's no peroxide, so this follows Markovnikov's rule. We have two hydrogens here, none here. All right, so this is the product, 1-bromo, 1-methyl cyclopentane. Okay, what do we get when we add water that's catalyzed by acid with the product? And this also follows Markovnikov's rule. We're adding H and OH. Okay, so this side gets richer. This side gets the OH. Okay, this time, what's the missing reagent or missing steps? Okay, how would we convert methylene cyclopentane to this alcohol?
Does that say OH at the end?
Right, this is anti-Markovnikov addition of water. And so we would use BH3THF, okay, followed by H2O2 and OH minus. Right. How would we make methyl cyclopentane from methylene cyclopentane? I'll give you a hint. Okay, so we've added 2 more hydrogens. So we would use hydrogen gas, and then we would need a catalyst, either nickel, palladium, or platinum. Catalytic hydrogenation. Okay, I want you to show me the product here, and also show me the stereoisomer that would predominate. All right, so we're adding hydrogen. Okay, so both hydrogens are added to the same side, so we would get the cis isomer. Okay, so we've got bromine and methylene chloride. Methylene chloride is just the solvent. Okay, what would the product be with the correct stereochemistry? What product would we get here? All right, the 2 bromines are going to add trans to one another. So we'll get this plus the enantiomer. Okay, so this gives anti-addition. Okay, this is what we did in lab last week. Not with this compound, but with a 6-member ring. Cis butene. If we react this with MCPBA, which is this, okay, what's our product? right, one of the byproducts is this. Okay, this is epoxidation. This is what we're actually going to be doing tomorrow. Okay, so the byproduct, or the main product, will be the epoxide. Okay, we'll form this three-membered ring. We'll add an oxidant across the double bond. And okay, since the methyls were cis in the starting material, they'll be cis in the product. Okay, so both of these are added to the same side. Okay, this is called epoxidation. Okay, we're going to do epoxidation of the double bonding cholesterol tomorrow. Okay. Show the product from osmium tetroxide and hydrogen peroxide. Okay, this reaction is stereoselective, so we get a particular stereoisomer. Right. This will give us a vicinal diol or a glycol. The two OH groups will be added cis to each other. All right, the other way of accomplishing this is to use cold dilute KMNO4. Okay, both osmium tetroxide and dilute KMNO4 gave us the cis diol. Okay, what if we wanted the trans diol? Okay, what we would do here is we would first do an epoxidation, okay, like with MCPBA. Okay, and then we could do either an acid or base catalyzed ring opening. And using water and dilute acid, we can open up that ring, and that gives us the trans diol. Okay, that plus the enantiomer. All right, what if we reacted this alkene with ozone, okay, followed by zinc or dimethyl sulfide? Okay, what would that give us? Okay, so it's this is called ozonolysis. The suffix olysis means splitting. So we're going to split this with ozone. All right. Split this. And we'll get two carbonyl compounds. We'll replace that CC double bond with two CO double bonds. All right, one more. Right, again, we would split here. Open up the ring, we would get two aldehydes. If we had carbon groups here, then one or both of those would be a ketone. Okay, that's all of our time, so I'm going to go ahead and stop there.